All right, here's page 13 in our notes. We read that this corporation, Pineapple Corporation, maintains that their cans have always contained an average of 12 ounces of fruit. So they make canned fruit, pineapple, I assume, and they say that there should be 12 ounces of fruit in there. The production group, so these are the people who actually make the cans or make put the pineapple in the cans. They were put there in a can with it's a different song. The production group believes that the mean weight has changed. So they think, for some reason, they've been sort of hefting these cans around. They're like, man, these feel a little bit heavier than they have, for the past million years. I think something's different. Or maybe they feel a little lighter. We don't know because it says they've changed, right? So that's kind of the first thing we want to point out is it has changed. Oh, whoops. The drained weights in ounces of sample. Oh, so the drained weights in ounces for a sample of 15 cans. Okay, so they took 15 cans, they drained them, they weighed them. On average, they got 12.09 of the 15 cans, with standard deviation of 0.20. So use an appropriate hypothesis test to determine if the data show evidence of a change in mean weight. Use a significance level of 0.01. All right, so let's go through these steps that we have reviewed. So step 1, remember, was to develop a hypothesis test and determine if it's one or two-tailed. So the hypothesis, we have H naught and H A is the alternative, null and alternative, right? So what's our null hypothesis? Well, the null hypothesis is the status quo, what sort of the historical value, that nothing interesting is going on. We're dealing with means here, right? Average of 12. Right? We took means, the mean weight, right? So we're not talking about proportions, we're talking about means, and so in which case we're talking about mu's. So in this case, we believe that the mu is 12 ounces, and always has been. Our alternative, though, is that we believe that it has changed. So we don't know which direction it's changed. It's just changed. So that's not equal to 12. All right, so is this a one or two-tailed test? Well, it's a two-tailed test because it's changed, which means we don't know if it's got smaller or if it's gotten bigger, right? So two-tailed. All right, so step 1's done. Have that done. Step 2 is to go collect some data, which has already been done for us. Calculate the sample statistics, which we've already done. So we have a sample of X bar of 12.09. Sample standard deviation, or S, of 0.20, and we have just write it down, and N equals 15, right? So we had a sample size of 15. And then since we're dealing with means here, we have to calculate a T statistic, right? Because we're going to use this in a minute. So let's just go ahead and do that. So the T, if you remember, equals this X bar minus mu naught divided by S over the square root of N. So X bar, let's just put this in X bar. I wrote it down just right above it. It's 12.09 minus, what is this, mu naught? Well, it comes from our H naught, right? So this has an equal sign in it somewhere. So mu equals 12, so that's it. So 12. And that we divide S right here, 0.20, sample standard deviation, divided by the square root of N, which is rather square root of 15. All right, so we plug this into our calculator or to an Excel or something, and I've already done it, so we don't have to do it, but it's 1.74. This is our T statistic. So we can sort of already think about this. This means that our sample is only 1 3/4 standard deviations away from an expected mean, which isn't too far away. And we already know that to get a pretty low p-value, you have to be pretty far away from the mean. So you can already kind of guess that the p-value is not going to be super low. But we'll keep going anyway. So here we go. Step number 3. Step number 3 is to set alpha. All right, is to set the alpha. Well, it told us what alpha should be up above. Let's go up here. It says right here. Use a significance level of 0.01. Significance level, and you see this in the notes, is alpha. That is alpha. And we call it significance level because we say if something is smaller than that, then we say it's significant, right? Statistically significant. So that's why they call it significant level, but it's really just alpha. Right, so alpha is equals 0.01, says so in the problem. Number 4 is find the p-value, right? find the p-value. Find the p-value. So how do we do this? Well, we know it's a two-tailed test. We know we're going to have to deal with t's because we haven't calculated t in step 2 because we're dealing with means. So we can go look in our notes and say, well, we're just going to use this t-dist function. But since it's a two-tailed test, there's a specific one in 2010 that we can use. Equals t dot dist dot 2t, two-tail, right? And in this, all we have to do is put in our t, which is right here, 1.74. 1.74, right, 74, comma, and then it wants n minus 1. Well, n is 15 minus 1. And that comes out to 0.1032, 372, or something like that. Doesn't matter. Something close to that. So let's give it a try. Let's, whoops, wrong one. Do it quickly. I wasn't prepared for this. Here we go. So let's just do it. Equals t dot dist dot rt. Before I do this, let me zoom in a little bit so we can see what's going on a little better. How's that? Equals t dot dist dot rt. It just wants x, and our x was 1.74. And our degrees of freedom, which is n minus 1, is 15 minus 1. Hit enter. Oh, see, I got a different answer than what I wrote down. Oh, because we're not doing a right tail. Oops. See, I wrote in RT. I want a 2T. So don't make a mistake like I did. It should actually be twice as big as what we just found. So it should be close to, well, that one was like 0.05, so it should be close to 0.10, right? That's what we found. Yeah, 0.1037. So be careful, don't put in RT when you mean 2T. So there you go, that's it, that's all you do. So remember, this is a probability of a t distribution, whatever is on the two sides, the two-tail. So it adds up the probability of both of these things, the chance of it being in there. So we have a 10% essentially chance. Let's go back to this. So that's step 4. Let's finish up with step 5. Step 5, maybe the most important step. What's the conclusion we make? So, conclusions. We say, since 0.10 is greater than our alpha of 0.01, so this is our alpha. This is our p-value. Remember, the rule says that if our p-value is less than alpha, then we reject the null. In this case, so we can't reject the null. We can't reject the null. So what does that mean? Well, we say that there is not enough evidence to say that there's been a change. So we say that more specifically, that the mean, that the mean has changed. That there has been a change in mean. A change in mean. Alright, we say this because we have a relatively high p-value. I mean, it's not too high, but it's pretty high. There is not an alpha that would normally be used where this would cause us to suspect. However, this is a two-tailed test, and we actually showed that if I just did a one-tailed test, right, if I just assumed that this 1.74 was just for one tail, this might change a little bit. It would be closer to 0.05, which again might be significant under certain conditions, certain alpha. But if I have a small alpha of 0.01, it's still not going to be significant. All right, so that's that problem. Let's go on. Let's take a pause here. All right, a healthcare provider claims that on average they don't overcharge for service. So on average, so sometimes they might, but other times they undercharge. So on average, they're exactly right. That's what they're claiming. So this is like a doctor's office or a hospital or whatever claiming that they don't overcharge on their service. But an insurance company is skeptical. So the insurance company has to usually foot the bill, at least for part of these things, and they think they're being overcharged. So they use sample data to prove their belief. So they go and sample, or really audit. It says audit 36 claims that were collected, and they find a sample mean of overpayment of $4. So on average of these 36, they were overcharged by $4, or overpaid actually. So they're already processed, but it's the same thing. $4 with a standard deviation of $12. Pretty big standard deviation. Suppose we can tolerate a chance of 5% rejection of the claim when it's true. Can we conclude that the insurance company was overcharged? All right. So let's do this. First step. Step 1, null and alternative hypothesis. So what's the null here? Well, we're dealing with means. We know that because we go calculate sample mean, and up here we can say other times they're undercharged, and so on average, they're exactly right. So we're doing on average, right? On average. So these are means, right? So means we're talking about mu, the mu, and they say that it's exactly right. So the mu of overcharge. What's the average overcharge? The average overcharge. The healthcare provider is saying is equals to 0. There is no overcharge. Sometimes they do it, but other times they undercharge. So on average, it's exactly 0. Essentially, what it's saying. What the insurance company is saying is no, it's actually bigger than 0. Right? You are overcharging me, sort of all the time, or more than 0. The average is greater than 0, essentially, right? So this is what we have here. This is a one-tail test, right? Because we only care about if it's overcharged, if mu is bigger than 0. So we're going to sort of draw some distribution here. We have 0 is the mean. This is according to this. This is the x bars, distribution of x bars. And the insurance company thinks, well, you're somewhere over here. We want to know what the real probability is of actually going on over here. Right? So one tail test on the right side. Right side. Okay, so I wrote down tail. Right there. Step 2. So step 2, we have to go and actually sample some data. We already did that, and we found that the average overcharge, or x bar of our sample, was $4. Right, so on average, the overcharge was $4 with a sample standard deviation of 12. And we did this with 36 claims, right? 36 claims right here, 36 claims. So then we have to go calculate a t from this, right? So it's not too hard. We know how to do this now. So t equals, was x bar, so 4 minus mu naught. Well, mu naught should be 0, right? According to our h naught up here. I can't see it anymore, but our h naught. All of that divided by s, which is 12, divided by the square root of n, 36. So it turns out that this is up here is 4, this down here, 36 is 6, 12 divided by 6 is 2. So this equals exactly 2. So this is a nice, pretty math problem. All right, so we have this is our t-score. T-score is 2. So again, what do we think about this? Well, this is 2 standard deviations away from the mean. So this is getting out there a little bit, right? Because we know that within 3, that's 3 plus or minus, the mean plus or minus 3 is 99%. So 2 we might start being a little nervous, but we're going to figure out with the p-value whether or not we really think we should. So step 3 is alpha. All right, we set the alpha. Well, it actually tells us the alpha up here. Suppose that we can tolerate a chance of 5% of rejecting the claim when it's true. So that is the alpha, 5%. Oops. So I didn't write very well, but let's see. Let's change colors. So alpha is 0.05. Okay. That's it for step 3. So step 4, we can find the p-value. So in this case, we're going to know this is a one-tail test. In fact, it's a right-tail test. Right? We drew the picture and we say that it's on the right tail. So we can just use the right tail, the formula with the t-dist, t.dist dot rt, right tail. And in that you put in your t, right, 2, and your degrees of freedom, which was 36 minus 1. And that's it. So this, we can go do it real quickly. Let's go do it. Oops, let's do that. This guy. So we'll do it right below the one we just did it on. So equals t.dist .rt, right tail, not two tail, right tail. Our x is really a t score we put in 2, and then 36 minus 1 is just 35. And we get 0.0267. 0.0267. Okay. 0.0267. So that's pretty small, actually. So what do we do with step 5? Well, alpha, remember, is equal to 0.05. 0.05. And we got a p-value of 0.0267. So what does that mean? Well, 0.02 is less than 0.05. So here it is. So we reject the null hypothesis. Okay. I'm not going to write that again. So we can conclude that the insurance company was overcharged. You know, maybe not by very much, $4, but it's significantly more than 0, right? Whether or not it's actually really a whole lot more than 0, that's a different question, but it's significantly different, meaning that from our sample, we found that the results of our sample were not just due to chance, right? But there really was a difference from 0. In fact, the average was $4. So there you go. So that's that one. So let's go to the next one, final one here. Is a little bit different than anything we've done, but it shouldn't be too crazy. In fact, it's already sort of worked out for us too. But let's just read through it. So, market research consultant hired by the Pepsi Cola company is interested in knowing if the proportion of consumers who favor Pepsi Cola over Coke Classic is different than 50%. Different than 50%. A random sample of 250 customers. There's our N. From the market editor investigation report, and 0.464% preferred Pepsi in a taste test. Using a 0.10 level of significance, this is alpha, level of significance, test appropriate hypothesis to test this question, to help answer this question. So here we're not dealing with means before we go about further. We're talking about, this is a result of a binomial experiment, right? So they go and ask people, do you like Pepsi or do you like Coke? Those are one of two choices. You only get one of two choices. And so Pepsi thinks that, well, they want to know whether or not people who favor Pepsi over Coke is different than 50%. They don't say if it's greater than or smaller or less than 50%. They just want to know essentially what's their market share. And they think their market share is different than just half, right? That's just the null hypothesis. Well, we have exactly half the share. There's two big customers or big consumer producers out there, and we want to say, do we have sort of more of the market share or less of the market share? We just want to know where we're at. Different. So we would sample 250 consumers, and we found our own proportion of 0.464. So this is our p hat, right? We want to say, is this, the 250.464, does that actually give us enough evidence that we're actually less than 50%? So this is, again, already been written out. But here we go. So our null hypothesis is that the true proportion is equal to 50%. Right? Our alternative is different than 50%. This is what they're trying to find. Right? Trying to prove. Right? Trying to find. Oops. And this is a two-tailed test, right? So this is going to end up being normally distributed. In fact, we don't even have to mess with t's anymore because this is a proportion. And if we have certain conditions for proportion, generally if our sample is pretty big, and it's the 250, it's really big, then we can say, yeah, we can assume this is normally distributed with the mean equals to 50, right? And what we're really interested in knowing is if it's really out here or if it's really down here. If it's in either of these tails, then we're going to be concerned. Two tails if it's changed, right? Two-tailed test. Okay, so let's do this. Step 2, we go get some data. We figure out our p hat is equal to 0.64 and our n is equal to 250. We could go calculate this z. We don't really need to because we're going to plug this into norm dist later on, but we could, right? And all it really is point. So it's just what p hat minus p over the standard error, which is what? P times 1 minus p over n, all that square rooted. So this is just going to be what, 0.464 minus 0.50 over 0.50 times 1 minus 0.50 divided by 250. Handwriting's too bad, sorry. All of that. So that all ends up equaling negative 1.384. So we haven't ever really gone and calculated a z before when we've done this norm dist, and that's because the norm dist will just do it for us automatically. So we don't really need to do this. This is from some other sets of notes teaching it in a different way. But just so you know, it's the same kind of process that we've done with the t stuff, right? Set alpha equal to 0.10, so that came from up here using a 0.10 level of significance. Finally, find this p-value. So here's a p-value, just gave it to us. So let's figure this out. How would we do this? Well, this is a two-tailed test, and we know that our p-value is smaller than what was expected. So it's actually, if I were to draw the picture, 0.50. We got some observation over here, 0.464 on the left side. So what we need to do for a two-tailed test is find the probability of everything left of that and then just multiply it by 2. And it will give us both sides. Okay? So we know how to do it in norm dist, how to find something to the left. Right? It's just a regular old norm dist, nothing special. So let's do that. It's going to end up being 2, we're all done, 2 times, let's see, norm dist, norm dot dist, either way, norm dist. We put in what we got, 0.464, what we expected, 0.50, and the standard error is this guy right here. Alright, just the bottom. I'm not going to rewrite it. We'll do it in 1 second in Excel, and then we'll know how to do it. And then comma 1. Alright, so let's go ahead and just do it right now. Let's see. Okay. So let's just write these things down. Here's p hat. P hat was 0.464. Our p, or really our p naught, was what, 0.50. So we need to find the standard error. Let's just find it first. We could find it, in the formula, but that's okay. Standard error equals the square root of p times, let's see, 1 minus p over 250. I should have written down n somewhere, but that's okay. Okay, so there's our standard error. And then for a two-tailed test, using proportions, now we can stick with the norm dist because we're dealing with proportions here, not with sample means. We can just use the norm dist. So it equals 2 times norm dist. Our x is our p hat. Our mean, what we got is right there, is our p. Standard deviation, we're really using a standard error. And then 1. 0.2549, so is that? Hopefully that's what's, yep, 0.2549. So that's all there is to it. So the only thing that's different here than we haven't had to do before is we have this 2, we're multiplying it by 2 first, right? And that's because we're concerned about both tails here, not just one tail. Because the two-tailed test, we want to see whether or not if it falls on either of these two sides, then we have to multiply it by 2. So we know in this case, in fact, you'll know all the time once you go collect your data, that it's on the left side. Right, so just find the left side. If this ended up being like 0.7 and it was on the right side, then we have to find what's on the right side and multiply it by 2. So that would be 2 times 1 minus the norm dist, so we can get the right side. Right? So that's sort of the easiest way. In the notes, it has this sort of complicated thing of figuring out the min of the, whatever is smaller or right or sort of left or right of things. It's easier to just sort of intuitively see, oh yeah, this is a smaller number, so it's got to be on the left side. All right, back to the notes. So step 5, we make conclusions. All right, so since 0.25 is, greater than 0.10, we cannot reject the null. Right? Cannot reject the null. So we conclude that by assuming that the proportion of people who prefer Coke over Pepsi is equal to 0.50. So we don't have any evidence that it's not. Right? Our sample doesn't give us enough proof to say that it's any different than 50-50 at this point. Right? So we could go take a bigger sample And as we get our sample bigger and bigger and bigger, we might actually find out that 0.464, and the mean still stays at 0.464, then that actually might become significant. If with a larger sample, it still becomes the same. All right, so that's it for these notes, I believe. All right, let's see. Let me double check. Yep. Okay, so see you in class.